coming to another week of the Foundations for Probability seminar. Today we have the great pleasure of having Professor Aris Spanos to come and speak with us. Professor Spanos is the professor of economics at Virginia Tech. And I happen to have the great pleasure of having spent 2 weeks at the summer seminar with Professor Deborah Mayo and Aris Spanos and learned about severe testing over the summer. And Professor Spanos recently just authored a book that came out, Probability Theory and Statistical Inference, Empirical Modeling with Observational Data. And today you will be telling us about the replication crises and the untrustworthiness of empirical evidence. All right, please welcome.
If I can just go to the previous slide. This is to tell you that I've been a statistician at heart. And I was trying to get my econometrician friends to stop care-feeding and looking at goodness of feed and celebrating they have excellent models. So the title of the first book tells you exactly where I'm coming from. And the idea was to rewrite econometrics by bringing out the assumptions people impose on their data and make them testable. Because in econometrics, everything is about the error term. Nobody has ever seen it, so you say to should whatever you like. So I was, of course, very optimistic, and I wrote the second book, lower level, where I explained everything with less formalism, but still wasn't convincing enough for at least econometricians. And the third one is a second edition of the previous one, but I changed one word. Instead of econometric, it's empirical modeling. Because the book has nothing to do with econometrics as such. Some economics examples, but that's about it. And the data are not exclusively data from economics or economic data. So here I have a list of topics that I could have gone through thoroughly if I had 10 hours. But since I have an hour or thereabouts, I want to show you what the paper covers. And in the questions, if you're interested in a topic that I don't have enough time to discuss it, you can pick it up. So the first topic would be my view of the replicability crisis. There is this automatic jump from non-replicability to untrustworthiness. I'm going to show you empirical examples. It doesn't follow. Because the source of the problem is not just abuse of the p-values and multiple testing and things of that sort. It's a much deeper problem. It's just one of the symptoms. And the extent of the untrustworthiness in econometrics cannot be explained by multiple testing and abuse of p-value. There are roots deeper than just misinterpretations. And I'm going to give you a very brief glimpse of what Deborah May and I call the error-statistical perspective, which is a kind of refinement extension of the Fisher neyman-pearson frequentist inference thing. So we introduce additional distinctions there in order to delineate a lot of the issues that are now confused. Of course, I cannot do justice to that, but the two distinctions I'm going to bring out is the modeling versus the inference phase set. And of course, the statistical versus the substantive models. In my field, that's a major problem. People in economics, especially macroeconomists, know exactly how the macroeconomy works. They have these beautiful equations, nonlinear and everything else, and you try to get them engaged, and they tell you, no, I know exactly what's going to happen, and you tell them, well, go ahead and predict next quarter. And then it falls apart. And their justification is, well, we can't really predict human behavior. No, there is much more to it than just predicting human behavior. And the reason is they're doing care-fitting. They come up with 8 nonlinear equations, and they spend hours and hours trying to figure out ways to estimate the parameters, and then give us a story that goes with it. And of course, it's just nonsense. And I have paper after paper debunking this way of looking at it. If you separate the statistical model, which is nothing more than the assumptions you're imposing your data, probabilistic assumptions, separate that from your substantive model, then you can make headway and figure out where your model is weak and where it needs strengthening and so on. If you mix them up into a big soup and you get a bad model, you don't know whether your theory is to blame or the bad assumptions you're imposing on your data. And that's the reason why that is there. The extension is what we call sort of going beyond the accept, reject, and the p-value. How do we go from that to an evidential interpretation of the results? It's missing. Many attempts have been made. There are many misrepresentations of p-values and all of that. None of that will get us out of that mess. We need an extension which takes into account the context. The context in statistics is a statistical model, a set of data, a framing of the hypothesis, the sample size, and so on. If you take accept, reject, and the p-value out of that context, it's a silly number. There's nothing there that can be turned into evidence. And I'm going to try and make a case for that. Now, part of the problem is that you statisticians are not doing a very good job of explaining a lot of these fundamental concepts.
You mean we, not you.
Let's say
Okay,
we're all in the
just
same boat.
remove yourself.
No, I do my best. And the reason is we're trying to please undergraduates who have absolutely no background to understand statistics where at the level they should be understanding it. So bringing it down and down and down and down, at the end of the day you have what one of my dear teachers used to call pre-digested pap. Nothing to do with real concepts and modeling and skills and everything else.
So do you feel we should quit teaching?
We should just force these undergraduates to do the work and understand that this is where at the level they should, not a sort of watered down version that doesn't really represent anything worth learning. So I single out 10 different issues that at this present stage make a mess of these discussions about replicability, trustworthiness, and everything else. There's no way I'm going to go through all of them. First is the role of the inductive premises of inference, what I call a statistical model. We really have to understand that at a level, a formal level, and not a sort of, here I have a model, here I have some data, and here I have an equation. There is more to that, and of course, it's the assumptions there that matter. And of course, statistical misspecification. Statistical misspecification is when some of your assumptions you're imposing on your data, implicitly or explicitly. Sometimes you have to do reverse engineering to discover the implicit assumptions. And the famous Yule actually did that in 1926 to find out what people are imposing when they calculate a correlation coefficient, and dug out the model. And then he looked at this data and says, none of these assumptions are valid. But he couldn't really frame it properly because it was too early. So I would put emphasis on that. And then, of course, the main objective and the reasoning. You might think that's obvious. We are trying to learn about this true set of unknown parameters we call theta star. Yeah, but then we forget when we start looking at estimation and testing. And of course, the underlying reasoning. There is a very different reasoning for estimation and a very different reasoning for hypothesis testing. One is factual, under the true value, whatever that happens to be. The other is hypothetical. What if theta 0 is what I'm interested in? And what happens if theta 0 is false? That's completely hypothetical. We choose those values. And it makes a hell of a difference in the inference and the interpretation and everything else. And of course, the biggest problem for psychologists, they cannot really get it into their heads that the observed value of an estimator is not anything you can say is very close to my theta star. You just cannot do that. Now, I've given...
Wait, you have at least 2 psychologists here. I think we would like to know what it is that you're saying we can't do.
Yes, you estimated a mean.
Yes.
And you implicitly assume that that value is representative. It's close to what you're trying to estimate.
Got you.
Okay?
X bar is close to reality.
You cannot do that. And if you do it, you get into trouble. There was some more trouble. for
Yes,
you.
yeah, you're right. You're
It's not
absolutely
a
right.
psychology,
That is
it's
exactly how the
everybody.
field is right.
That's not.
So, the other thing that I discovered early in my career when I was doing misspecification testing, people really don't understand when you're testing the assumptions of your model versus within the model. I have a model, I assume it's valid, and I want to learn about theta star. These are completely different things. And the testing you're using there is completely different. And I will explain that later on. Now, the frame of the neyman-pearson. Yeah, you might be interested in a couple of values in the parameter space. But for statistical purposes, the whole of the parameter space is relevant. Why? Because you don't know what theta star is. It could be in the part you left out. So for statistical purposes, partition the parameter space. If the null is one value or a subset, the rest is the alternative. That's the only way these tools can actually
You're
make
saying
sense.
theta star is your null? Is your null?
Whatever your null is.
Yeah, sometimes we know the exact values in medical applications. We know what the null we want to test for, whatever alternative.
But if you're assuming theta is between 0 and 1, and you only look at the values the medicine gives you, you jump in the gun. You jump in the gun. It could be any one of those values. Yes, you have a pretty good idea where it should be, but you don't exclude those at the outset. You bring them in when you should. And then, of course, the pre-data and post-data. Everybody uses the p-value not as a post-data, as Fisher meant it to be, but as a pre-data concept. Why? Because when they talk about, let's say, values of the sample worse than the ones we observe, they look at the alternative, the framing of the alternative, and then they come up with it. So a lot of people accuse Fisher, well, he must have had an alternative in mind. No, he didn't. He just looked at the value of the test statistic and the sign, and he knew one of the tails is irrelevant. It's a post-data concept. You have more information than the original. And then, of course, the long-run interpretation error probabilities. Robin was in that seminar, and it was very controversial. But when we do testing, we're using probabilities. We're not using relative frequencies. We're not using this metaphor of the long run. And the probabilities refer to this test and this data and this hypothesis. We have to separate the interpretation of probability from the tools. And of course, the worst thing is error probabilities are conditional. Sorry, psychologists make that. What conditional? You cannot condition on theta. Theta is an unknown constant. There's no formal way you can condition on hypothesis. But when you do, you shoot yourself in the foot, and you get totally confused because you don't know what you're doing. Error probabilities are under scenarios. The true value of theta for confidence interval, whatever that happens to be, or under the null and under the alternative, whatever those values happen to be. Scenarios that we evaluate sampling distributions. Nothing to do with conditioning in the formal sense. If you're a Bayesian, go ahead, do the condition. But if you're a frequentist, there's no such thing. And of course, the small n problem. Small n problem is if your sample size is not large enough to test your assumptions thoroughly, forget inference. You're just killing yourself.
This is the psychologist problem.
There is the, I don't know, but there is a large n problem which I'm going to focus on, which is leisurely later on. And then, of course, the post-data similarity evaluation. It supplements the frequentist testing setup to go from p-values, accept, reject, to an evidential interpretation by outputting the warranted discrepancy from the null based on this data and this test. It's local. It's not something that applies to other tests and other data. And I'm going to, if I have time, show you how you can basically scorch a lot of these, let's say, weaknesses of the neyman-pearson setup. Reversing the null and the alternative, 0.05 you reject, 0.4, 0.049 you accept. Nonsense. The severity is not going to change because it doesn't depend on C alpha or the alpha. It depends on the sign of the observed value of your test statistic. So those wash away, and then you have a clear interpretation. And of course, I want to think about, if I don't have experimental data, what does replication mean? Why? Because in econometrics, most of our data are observational. So we have to think about those issues. And I'm not pretending I have the answers, but I use an example to show you that in the case of severity, there is a sense of replication that I think is useful. So I use data from my native country, Cyprus, for the ratio of boys to girls, and do the severity assessment and everything else, and then go back in time. 1685, I use output node data for London with a similar sample size and say, well, let's compare the two warranted discrepancies from the null. Completely different time, completely different location. Do we get similar answers? And the answer is yes. And in both cases, those warranted discrepancies include the substantive discrepancy that we get from human biology. So that's what I have in mind, and I hope I can make sufficient. So here it is. The famous Ioannidis, most published research findings are false. And of course, the culprit here turned out to be the significance testing in general, and of course, the p-value in particular. And people began to propose reforms. So we have replacing the p-values with observed coffee residuals, thinking that they have different information. Using estimation-based effect sizes instead of testing. But if we have to use testing, we have to redefine what we mean by statistical security. Now, I agree with absolutely nothing there. And I will try to make a case that all those suggestions are actually based on severe, in a different sense, confusions that are deep-rooted in this literature. So, let me just put my cards on the table by stating a few things that I find not, let's say, lopsided and misleading. First, the focus of the current discussions is on experimental data. You can't really take it very far in fields like mine, and so we have to rethink of that. Then, blaming abuses of significance testing. And here I include the p-hacking, the multiple testing, the cherry picking, the low power, and everything else. Although very important, is too narrow to explain the extent of their trustworthiness. So how do I know that? For 8 years, I had an army of 50 graduate students each year. And I will assign a famous paper in my field, applied paper, to each one of them. Their project was reproduce the original results as closely as you can get, then test the assumptions these people are invoking when they use their t-test and their f-test and their chi-square test, whatever else they're doing. And you get a 75% if you reach this far. If you can respecify the model to ensure that the assumptions are valid, just change it in directions which includes the original, and you tell me how the original inferences change, you get 100%. So 50 people, 50 papers each year, 8 years. How many papers do you think in the published papers by Nobel Prize winners, most of them were these papers, survived that? 0. They didn't even come close. It wasn't just one assumption it was valid. It was 5 or 6 out of 6. So that's how I learned that statistical misspecification is really a terrible problem, and I have to do something about it. So, statistical misspecification, I'll show you what happens when one of those assumptions is invalid, and then you can judge how that works out if we have 3 or 4. Then, of course, confusions pertaining to the abuse of concepts in frequentist inference that just make a discussion impossible. And then there are these Bayesian undertones. Yeah, you're not really interested in what you get in frequentist testing, you're interested in attaching probabilities to data. No, I'm not. And I don't know what to do with those probabilities if I have them. So I want a very different, let's say, theme and interpretation of what I understand as evidence. So, my first argument, replicability is neither necessary nor sufficient for trustworthy evidence. I'll show you critical examples to back that up. Why? Because there are dozens of replicable but untrustworthy evidence, and trustworthy evidence are not replicable using lame procedures in my field. And dozens of papers already published. This is not reinventing the wheel now.
How do you define evidence and what is trustworthy evidence?
Well, I take, let's say, the inferential results that these people take as given as was what they consider as evidence. So every applied paper has conclusions, and those are what they think are the evidence that come out of the data. Argument 2. The widespread abuse misinterpretation of the p-value is only a symptom, and I have a much bigger culprit. The recipe-like uninformed implementation of statistical methods without real understanding of their assumptions, limitations, probability implementation, and warranted interpretations of the results. So it's a much bigger problem. Statistical misspecification, of course, is right at the top of that. Inadequate understanding. Yeah, I was giving a seminar in Seattle to a large group of psychologists, and we were talking about differences between two means, and I mentioned normal IID. 95% of the people there said, what? I said, these are the assumptions you are imposing on your data. And their reaction was, what assumptions? I mean, the formula is clear. I said, yeah, but the formula comes from you imposing assumptions. So that's the extent of the problem. And of course, inadequate the implementation. People just throw things into a computer package and just look at the result, take them at face value, and work their way to stories.
Before you go on,
Sure.
Your argument too on that previous one, I was going to ask you, have you found a mathematical statistician that disagreed with you in an argument?
I don't know. I think we agree, but what we should be debating is how do we cure the problem? I mean, if the statistics department is teaching the psychologists and the economists and these people, there must be a way to get at least the correct way of understanding and implementing this. And that's what I do in my courses. I mean, I force people to take data and try their luck out to see what can go wrong. Yes?
And I suppose the question is it the statistics department that's teaching the economics department and the psychology department, or do they have their own statistics courses at that point, or something like
Well, that's where you come in and you say, wait a minute. When is a psychologist teaching physicists? I mean, you need a certain level of skills and technical ability. So when I was a student at the LSE, I would never go to a mathematics course taught by economists. Actually, I did, but then I walked out and went to the mathematics department and said, shame on you. This person is not fit to teach functional analysis, and he pretends he can. Next year, there was a course on functional analysis taught by a real mathematician. So that's how you make changes. He was useless. I mean, I stood up and walked out, and halfway through he says, where are you going? And I said, I have much better ways of wasting my time than listening to you talking nonsense. And I disappeared.
I'm not sure I understood what you meant by trustworthy evidence that is not replicable.
Trustworthy evidence here refers to evidence that actually are based on your data and your analysis.
So why would it not be replicable?
Because if people misuse statistics, they never test their assumptions, and they use available models instead of thinking what kind of model will capture these regularities of data will never be.
But it's trustworthy, you say.
Different ways to trustworthy evidence, how you can get there. And
Well, you say,
they contribute to
so I'm asking for an example of trustworthy evidence that is not replicable.
Yeah.
I don't question whether there is one, but I
Yeah.
didn't understand.
Here it is.
What is trustworthy evidence that is not replicable?
Yeah. Here is testing the efficient market hypothesis for which somebody got a Nobel Prize. On a weekly basis, there will be 24 papers regressing returns on a particular asset, which is the YT, on past returns, and say, well, when the past returns are actually insignificant, then the efficient market hypothesis is valid. So this is what they do.
It's saying like there is something out there, but you're not using the correct
Yes,
test. to
here it
detect
is. Here it is. This is a US Canadian dollar. I have 952 observations. That is repeated every week by MBA students. Every week. They run the same silly regressions. They look at that and say, well, neither of those two coefficients is significant, so the efficient hypothesis is correct. And I say, no, let's just go back.
You're not
I
saying-
jumped ahead. So here is the efficient market hypothesis. This is Fama, who got the Nobel Prize a few years back. He basically, you start with a speculative price, a share, and you turn it into log differences, which is what they call returns. And then you basically say, these are unpredictable from their own past. This is the narrow efficient market hypothesis. So you say, okay, this is really what the old past, this is the past history of the process, and it's unpredictable, it's white noise. So you can't really make real money. So how do they test that? They come up with an regressive model. It doesn't have to be 2 lags, it could be more or less. And you say, if the coefficients of those lags are statistically insignificant, then they don't contribute anything, so you're stuck with a constant. And that you can take any asset you want. You run that regression, and you're going to get very similar results. The reason? Half of the assumptions they're imposing when they run that regression are false. Normality is completely false, and of course, homoscedasticity is false, and there is more. There must be a difference. There is dependence there. They are not picking up. How would you do a better job? Go back to all other distributions and say, well, what distribution will give me a heteroscedastic conditional variance? Because the normal will give me a homoscedastic one. I went for the student t distribution. Redid the whole autoregressive thing, derived the conditional variance, which is the heteroscedastic, and that's the model there. I don't give you the explicit functional form, but I could. I have a separate, and estimate that model. And both coefficients are significant now. Not only that, the sigma squared is considerably smaller, and of course, everything changes. Now, why don't people do that? Because they don't invent models like the student's T autoregressive model.
What you're saying is that, there is a true signal. It means something,
Yeah.
but we can't replicate it because we're violating the assumptions of the model we're using. We're not able to replicate that all the time.
Yes, and even if somebody gives you a hint that your normality, homoscedasticity, and the dependence is false, you're going to go back and patch up the original model. And that's where things go wrong. So I challenge people to show me another model which doesn't take into account all of these departures to prove that. So they use Garch, eGarch, Arch. Nothing happens. They get the original results because they're not doing coherent, let's say, modeling based on joint distributions and functional forms that you don't invent, but you get from the distributions themselves. So that's one example.
So when you said, I'm just trying to, so that when you said trustworthy evidence that is not replicable.
Yes, this evidence will never be replicated by a traditional econometrician or an MBA student.
So I was supposed to understand not replicable by those idiots.
Yes.
Yes. But replicable, but it could be replicable.
Because they narrow their tools to a specific set of tools that don't involve inventing new statistical models.
So that was the word that was missing, otherwise you would have understood it.
So I have many examples like this, by the way. I didn't have time to include them all. Yes.
So my question is that replicable, and then that's what is your definition, right? It's exactly as Glenn said. If you just use kind of naive way to do these things, definitely it's not replicable. If you do the same very careful way, you might be replicable.
Yes.
So the frequentist statistical modeling is that you do need assumptions. We only guarantee the replicable if you did the right thing. If you don't do the right thing, there's nothing is off the table.
Yes.
So that's not equivalent equations there.
Sure, but then you're forgetting something. People understand re-specification very differently.
Mm-hmm.
The traditional way is I patch up the original model, and they do. And you will never get the right answer.
Yeah,
that's the wrong replicability part. So
okay.
the context is really important here, because if the only tools they have for re-specification is to estimate the autoregressive function and then take the residuals and do another function for the autoscedastic function, they will never see these significant coefficients. Yes?
You just said you'll never get the right answer. How am I supposed to know what the right answer is?
The right answer is I test all the 5 assumptions that I impose on that model, and they are perfectly valid for my data. That's the right answer. All 5 assumptions. Functional forms, here I have students T, linearity of the autoregression, heteroscedasticity of a very specific form. I wish I could dig out the model so we would know what we're talking about. So permit me for a second to go to a different set of lecture notes to show you exactly what it's not here. Sorry. I have to go through a different route. This is the student's T ARP model. So you have a very specific autoregressive function, which is the same as the normal. But then there's, the scedasticity function is this thing here. It's not arch, it's not garch, it's not any one of those forms people do. Where do I get this? I go back to a joint student's T distribution and derive its first 2 conditional moments. And derive these parameterizations. This is a very important part of the issue here. So the same variance covariance matrix defines these parameters as well as the deltas here. It's not a separate modeling exercise. So I test these assumptions. I here actually have a student's T with 5 degrees of freedom. That's specific. Linear, heteroscedastic in this sense exactly. Then I have a Markov P process. Markov with P lags, and then I test the T variance, the constancy of these parameters. This is the most difficult assumption that you actually need to have a real model. Right.
We understand that in model checking, usually what happens is you have a test and then you fail to reject it. That means that your assumption holds. So does that mean that that's...
No, here I have 952 observations, a lot of power, and I reject every other variation of heteroscedasticity. Yeah, I have 15 different ones that come from different distributions. So here the rejection, the acceptance is not because I don't have enough capacity to detect discrepancies. That's why I use...
Ultimately, when you say that you think that the model the assumption holds, it still comes down to not being able to detect a valid alternative.
And I'm going to show you what you have to do to confirm that. And it's really auxiliary regressions that involve all kinds of things, joint tests and so on. This is not just a single assumption test. This is a comprehensive way of testing multiple assumptions at the same time and trying very different specifications ways that it can be wrong. I mean, there's a lot of thought
I
behind
guess
that.
that my question is just that we all know that models are never right. So to say that the model assumptions hold is at best an approximation to.
They're all approximations. If you're doing statistics and you're looking for precise results, forget it. These are all approximations. But if you make sure you have a large enough sample size and powerful tests to detect discrepancies from your null, then you say, here it is, here is my data, you go ahead and do your best to discover that any of these assumptions are invalid.
All models are wrong, but some are useful.
No, what I'm saying, well, yes, but what
But
I'm
in a
saying is
different
when it
sense.
comes
We're going to come back to
when
that
it
in a
comes to
second.
assumptions, a lot of times the assumptions are usually just left as assumptions. Sometimes they're testable, sometimes they're not. And
Half of my research time over the last 40 years has been, let me tell you exactly what you're assuming, and let me tell you exactly how you can test these assumptions in the most, let's say, trenchant way. That has been there's no assumptions about errors. They're all assumptions about X, Y, and Z. We observe them, and we know how to really detect discrepancies. It's not about, I cannot test this assumption. There's no non-testable assumption, because that's not a well-defined statistical model.
So do you have any concerns about overfitting?
Absolutely. Overfitting will actually appear as misspecification.
So, I mean, like, have you introduced a lot more parameters than the wrong
Yes.
models?
If you choose the number of blacks here, on statistical adequacy grounds, I guarantee it would be much smaller than Archaigi and BIC and Harlan Queen and all these other things. Because statistical adequacy will tell you, you don't need another lag to mop up the dependency in the data. Or you don't need another trend to capture the heterogeneity in the data. That's the beauty of having assumptions about the observables and not the other terms.
Before you move on, can I ask you this question? If the model is right, and as a frequentist principle you're going through a use frequency method, you will have a replicable, reproducible result. If everything is perfect, ideal, you did analysis right, your model is very good description of your data, and then you think in this type of the practice, just using frequentist principle, whatever you do, and then the right way to do data analysis, will that be result is reproducible? Just
Yes. If people ask me, how did I come up with this model, then that would be reproducible.
Okay.
But we need to agree on a common framework
Exactly.
to be
Okay,
able
so
to
yeah,
reach that.
it's just the practice. In
Okay.
practice currently,
Yes,
there's a lot of mistakes, so that's not reproducible. It's not because of the principle.
I totally agree, but
Okay.
I'm looking at a certain setup now
Okay.
and saying, let's think about what we can do to avoid some of this. And of course, I'm going to leave those behind. This was one of the examples I have. I have several, by the way. And then let me talk about the error-statistical perspective very quickly, so we don't spend too much time. I already talked about refinement extension, and here is how we refine, let's say, frequentist inference by enlarging, let's say, the choice of the original model. Yes, I'm going to look at the data plots, the questions I want to ask, because both of them play a role, and choose a statistical model. First stage is point estimation. I have an estimated model. But the second one is trenchant misspecification testing of the type that I will show you examples of. Now, if any of my assumptions are invalid, I specify. With, of course, the aim to capture the regularities the original model didn't. Only when I have a statistically adequate model, I go on to do inference. If I jump the gun, I'm going to shoot myself in the foot. So, when I'm debating with my colleagues who are very suspicious of what I'm doing, I say, well, think of modeling as constructing a boat to a given specifications. It's the construction part. And then the inference is sailing it in a competitive race. You cannot confuse the two. Yes, if you don't do a good job with the specifications here, you're not going to do very well in your inference. But confusing the two is deadly. So think of yourself in the middle of the ocean with a huge pile of wooden piles, and you're trying to construct it while you're racing it. Doesn't work. Separate the two sets. Why? Because inference says, assuming the model is valid, this is an optimal test. That's how we do it. So do your best to make sure your model is approximately valid. We're always talking about approximate validity.
In some fields, people have felt that the modeling should not be done with the same data as you use for the inference.
Yes.
But here you seem to be doing that?
Yes. No, I'm not. In my field, if I have quarterly data, I will have, let's say, 200 observations. I don't want to screw half of them for playing this game, because the power of my test, both the misspecification and the inference part, will be much lower than I have. So this separation sounds like a good idea, but you're getting considerably less precise and powerful inferential procedures if you do that. So if I had 10,000, yeah, I'll do that. And I won't have any difficulty doing it.
But also that the data are remodeled when you're testing the particular statistical hypothesis within the model, remodeled from what it was when you were using the data to test the model. I mean, insofar as the error probabilities of tests of assumptions work, you actually remodel the data. So for example, you know, you look at residuals and so on. So even though in some sense it's the same, they're actually modeled differently.
Could you go back to the previous slides?
Particular outcomes versus, let's say, average.
So the misspecification test, you're using the same set of data.
Yes.
Okay.
But you're posing completely different questions to the data.
Right.
I actually have a formal result published where you have a minimal sufficient statistic and a maximal ancillary statistic, and the misspecification. That's why we use residuals, because they are these maximal sufficient statistics. And then they enable us to actually do that separation without infecting, because theta is not part of the ancillary statistic at all. So whatever is the true theta plays no role in the misspecification test. I can send you the paper.
Okay, good, thanks. Yeah.
Now, just to show you how involved this process is when you want to bring out all the assumptions. As an econometrician, I was taught linear regression course. So I start with a set of assumptions, and then 20 pages later, I said, but there is this other assumption. No omitted variables, and then there is this other assumption. No observation errors, and this other. So wait. If I want to establish statistical accuracy, I need a complete, internally consistent and testable set of assumptions. Nothing else will do. So here I have what I did with the linear regression and the Gauss-Markov plus the normality assumption from errors to observables, and this is a very important part. This is what I'm estimating, statistically speaking, when I estimate a regression. My colleagues, they're estimating marginal propensities to consume elasticities and all. No. You don't jump to that before you can make sure that these assumptions are actually valid for your data. If they're not valid, you cannot use t-statistics to talk about positive, negative, and all the rest. Are they testable? All of them. And the tests I'm going to apply, let's say, they are not tests for single assumptions. I will have a test which involves linearity, independence, constancy of the parameters in the same setup. And of course,
what's the role of robustness? You know, sometimes I can change some of our assumptions. I don't need to have completely normal data. Central limit theorem.
We can talk about that. Robustness is one of those misused terms. If somebody tells you they have a robust result for heterogeneity in your data, trends and jumps and everything else, don't believe it. If somebody tells you that I have robustness towards dependence Don't believe them, don't believe a word of it.
I'm doing a simple t-test. I don't need normal data. If
That's the only thing we know, normality. And the least of your problems is this assumption. So you don't even test it before you make sure these assumptions are valid. Normality is a trivial issue here. These are the real assumptions. There are no robust results. Don't believe people when they sell you that. It depends on the type of heterogeneity, it depends on the type of dependence. There's no way you can, here, yeah, if it's bell shape, it's okay. If it's, let's say, symmetric, yeah, and you have a large sample size, yeah, it's okay. But none of these will save you. So let me go straight to an example, because I think this is the right time. I'm going to leave some of this out. Here, this is a simulation. So I play God, so we know what we're doing. Here I have a linear regression. The generating mechanism, because I generate the data, is this. And I'm going to estimate that model, which is the true model. What I do here is, I generate data with a tiny trend, 0.1. And then see what happens to my inference. Now remember, that is one of the 5 assumptions, or half of one of the 5 assumptions. It's about the constancy of the parameters. So if you have this trend here, your constant is not constant. But I estimate leaving out the trend. What happens? 10,000 replications, so I have plenty of replications here. Of course, I have sampling distributions when I do 10,000 replications of size 50 or 100. But I summarize it because they're very close to symmetric with the mean and the variance. So what is the mean with 50 observations, 10,000 replications, when I'm estimating with a 0? This is the truth. I nail it. The mean of the empirical distribution, not a single value. A single value can be anywhere. I need the mean of 10,000 such samples. Nail it, standard deviation, on the larger side, but it's 50 observations. What happens if I increase the sample size to 100? 10,000 replications again? Nail it, nail it. But remember, it's the mean. The standard deviation, considerably smaller. This is 0.5, true. Nail it, very small, totally nail it here, smaller, all the way to the R square, sigma square, and of course it improves. The most important of all, every time I draw a sample of 50 from the 10,000, I do a t-test. Remember, I know the true parameters, so I can evaluate the empirical type whatever. I know the true one, so I know if I reject the null, it will be on the side. And I calculate the relative frequencies here. So 0.05, 0.4, 0.049, 0.047 with 50 observations. Here I nail them both. So this is what it means, precise and accurate results. But of course I'm playing God. But it's the statistical adequacy that makes this happen. What happens here? I have a trend. I ignore it. I can show you data sets which don't have that going up, and so you can ignore it without realizing. The mean of this sampling distribution of beta 0, remember the truth is 1.5, is 0.4. What does that have to do with anything? Well, the best part is it gets worse when you increase the sample size. So when people tell you, I have a ton of observation, I don't have to worry about data, you say, yes, you do. There's no escaping it. There are misspecifications which get worse and worse as the sample size increases. One of them is heterogeneity.
Yeah, that's because when you increase the sample size, your bias doesn't go down, it stays there. The precision of estimating the bias goes down, as you can see here.
Yeah,
but the bias itself doesn't go down.
No, the sampling distribution of this parameter actually goes to 0. That's what it means. It doesn't go to the true no parameter you think it does. Here, the true is 0.5. I get close to 2. It gets worse. This converges to infinity. And of course, this is the famous R-square. When you have a trend, the real R-square is 0.25, you get 0.979. Why? Because you're taking mean deviations from a constant when your data are trending. So you blow up the denominator of the R-square. So for those who don't remember the formula, the R-square is 1 minus the residual sum of squares over what people call the total sum of squares. But if you're trending, your y is trending and it looks like that, and you say this is the mean, and then you take deviations from that and square them and sum them up, you get a huge number. So huge number here, tiny, you're very close to 1. Not because you have a good R-square or a goodness of figure, because you have a misspecified model. So all of these are trash. This is what happens when you have ecosystem estimators. This is exactly how this works. Here is the story. I'm doing a 5% significant level test. What is the actual time on error? 0.774 for beta 0 and 1 already. So I'm guaranteed to reject a true null hypothesis 100% of the time, period. With 50 observations. When it's 100, they're both 1. Yes, that's where unreliability of inference creeps in. You think you're doing a 5% significant level, so your C alpha is, I don't know, 1.96, two-sided, but actually it's not 5, it's 100. That's how easy it is. Remember, this is half of one of the 5 assumptions. And that's the result.
Yeah, but this is not going to happen, Aris, when we're going to teach it, because we have diagnostic checking, and this is going to show up there.
Yes.
When we do the diagnostic.
But it depends how you do the diagnostics. You see, that's the other thing that we have to do. When people use misspecification tests, they use them haphazardly. There's no coherent way you can actually decide. I have another example where you can look at the data and swear to God there's no trend. Then I show you there is trend. Serious trend. So this is just a glimpse of what happens. Usually it's 5, from the 5 assumptions, 3 of them are wrong, as in the efficient light hypothesis, not just half of one. So things are actually worse than what I made out here to be.
Can I ask you the question on the test?
Sure.
What is the beta 1 in the t statistic? Is the true value you put in? Is the
I know the true values. I generated the data.
It's just 0.05. You put in
Yes.
0.5. Okay, not 0. Okay.
And I deliberately have that very low. Because for statistical inference purposes, it doesn't really matter whether it's high or low. It's what it is. For substantive purposes, we are not explaining a lot of variation. And that's a different issue. So when I try to convince my fellow econometricians that omitted variables is not a statistical assumption, they wouldn't believe me. But it isn't. Statistical assumptions are the assumptions, probabilistic assumptions you impose on this data, not data you don't have. And if they're valid, you are in good company. So how does that come into the picture? This is where things go wrong in a more general setup. Every statistic, and of course that means function of the sample, gets its distribution, its sampling distribution, by going back to the joint distribution of the sample. The thing that defines a statistical model. There are 5 assumptions. If any one of them is invalid, you're going to get the wrong sampling distribution. Now, if you're a Bayesian, you can say, yeah, we're not doing that. Yes, you do. Because you define the likelihood function as proportional to the distribution of the sample. The only difference is you replace the generic with the observed data. That's the only thing. So if this is misspecified or wrong, it's going to affect the likelihood function, and of course it's going to affect everything else, even non-parametric. That's the other thing that people get confused. And of course, the RKD and all that are simply irrelevant here. So that's the bigger picture. So, yes, I have the RKD there. A real example here. This is the sleep aid Ambien. It was introduced in the early 90s. And there was a particular dose for everybody. And suddenly here in Europe, people realized that the number of accidents by young mothers taking their kids to school increased by 150%. And they were asking, what is the common denominator here? It took 10 years to discover that most of these accidents were actually got into by mothers who took Ambien the previous night. So eventually, they convinced the medical company that introduced to go back to the original data. And they said, well, we looked at ethnicity, we looked at sensitivity to a lot of drugs, we looked at a lot of other things, but we didn't think gender has anything to do with it. Well, here is the number of hours that takes a male to metabolize that particular dose, and this is the time it takes a female to metabolize the same dose. It was something like 7 versus 10. So any mother that took the Ambien at 10 o'clock or 11 o'clock, woke up 6 o'clock next morning, it was half asleep. It took another 10 years for the FDA to change the doses from males and females.
Wait, I'm confused.
Is that actually male and female, or weight, or?
Yes, there are different doses. 10 for the male, 5 for female.
That's what that's showing.
No, this is the number of hours to metabolize
The same dose.
the same dose. Yes.
Right, but I'm asking if the effect is actually male-female, or if it's something else, like weight.
Body weight.
Like if you weigh more.
They've in the trials, first phase, second, third, they tried all of this. They didn't think that male-female might make any difference. But when they went back, there was heterogeneity. Difference being, and this is not a trend, but you can see how the mean here is very different from the mean there.
But I'm confused because the difference between 7 and 10 is so big. It feels to me like no matter how crude and imperfect your statistics are, almost any statistic you would do, no matter how bad, would pick that up. You just have to do the comparison.
They didn't think it was possible. Somebody actually alerted them. In sort of halfway through, somebody published a paper and said, why ethnicity and sensitivity and not gender? Of course, at that time it was sex. But that's the point. They didn't do anything until it was basically pretty clear. They did some new trials and they figured it out. So my point here is that experimental data with the best protocols, the same procedures, are still vulnerable to statistical misspecification. Plot the damn thing. I mean, that's all it takes.
But no, but this is not a statistical misspecification. This is they didn't think to look.
It's a behavioral
Well,
misspecification.
Yeah, right,
It's how you order your data. When you talk about homogeneity or heterogeneity and dependence, it's the ordering that matters. In here, the ordering is male-female.
But how do you test this kind of misspecification without knowing that a priori that's a kind of heterogeneity?
Well, that's the point. When you do these trials, you have to think of all the different potential factors.
We're scientists. We don't know what the factors are, right? This is the issue.
Then
right?
you're going to get the answer wrong. Period. So
So we have to know the answer before we do the experiment. That's great. I wish I could do that.
No, you have to try it out.
Ben says that we can do that, you know.
You do a randomized trial, but you test for baseline differences before you analyze the data. You test
Conditioning on what variables?
No, you test
The
for
only thing you need
gender,
here
weight,
the ordering.
So we have to know all of
Aris,
the relevant
usual
conditioning
demographics.
variables to
Aaron
test.
was asking, don't they look at weight, didn't they look at weight? Because
Yes,
they
they
know.
did. They did.
Yeah.
Because when they randomized, they tried to make the two groups and weight irrelevant.
Yeah.
But they didn't think that
Gender.
gender could be
But
an
weight
issue.
wasn't enough?
What about shirt?
No, the weight wasn't enough. I mean, they had
serious,
pretty
like-
closely comparable subsets, if you like.
Barometric pressure.
It could be. You never know how it is. But as I said, somebody alerted them 5 years after they introduced it. So it wasn't that nobody thought about it. It's just they didn't do anything. So the question is, having seen these implications of statistical misspecification, why are still people not testing their assumptions? Now, I have a
Sorry,
whole paper.
what assumption could you test without knowing a priori that gender was
The mean time of metabolization is constant.
across
Yes, across.
what?
Well,
What if you
the patient.
what if you shuffled the patient identifier?
Yes, you're not going to
And
see
then how would
it.
you
You
detect
need the
that?
ordering.
You get something that's kind of bell-shaped, right? You need the ordering to actually
Yes.
respect whatever the underlying causal variable
That's
is.
the point.
But if you don't know what the causal variable is, how can you possibly hope to test
When
it?
you have cross-section data, there is not just one natural ordering you should worry about, like time series. There are 3 or 4 or 5. You have to think about potentially these kinds of issues. So,
I mean, I am a psychologist. We are thinking about these, but we don't know what they all
No,
are.
but if you
And-
if you do a histogram,
then you get it wrong, and that's what I'm saying.
if you do
But
a
it
histogram,
sounds like we're just fucked, right?
No,
Like,
no.
there's no way to detect when we're
No.
wrong unless we know all the potential ways in which we could be wrong.
You could do pre-trials, and in order to find some of these factors you should worry about, if you do a good job with your randomization and everything else. I mean, there are ways to find out. And as I said, somebody 5 years later publishes a book and says, you did that and that and the other, but you never really brought change.
if you do a histogram over time, metabolization time, you're going to get a bimodal,
Yes, you can get
bimodal,
some.
not a single
Yeah,
distribution.
it's not going to be totally symmetric here, but still, it's not going to give you enough. The ordering is important. So
Good.
don't believe anybody who says, I have cross-section there, I don't have to worry about dependence and heterogeneity. You do. You just have to think harder. That's
It's going to be bimodal because you have two groups.
In this particular case, though, sex is like, how could they not have looked
You
at
get
it?
involved and you have let's say, a smaller middle section. It's flat. I did it.
Is it fair to say that you are recommending p-hacking?
Yeah, that's what it sounds like.
At the stage of constructing your model, not the inference part, you can do all kinds of things. Because you're not using error probabilities to do inferences. You're just filling your data and seeing whether certain assumptions might be ballpark okay and other assumptions, so you will know how to test them. See, you get hints about these things, but orderings are very important. So I have a whole paper, and it's 35 pages, 50 reasons why people tell me they don't test their assumptions. The one thing you have to be very careful about is when people use robustness claims, so Prakash already jumped to that, and they use optimal asymptotic procedures. Here I have perhaps the most able probability theorist in the Berkeley group, writing a book on asymptotic properties. He starts, limit theorems, as n goes to infinity, are logically devoid of content about what happens at any particular n. Period. It's invoking the afterlife. Nothing to do with what you're going to do here. He said, goes on. All they can do is suggest certain approaches whose performance must then be checked on a case-by-case. Unfortunately, the approximation bounds could get a very, or too often too crude and cumbersome to be of any practical value. If anybody, like Glenn, read James Bernoulli's book, he tried his golden theorem to make it practical, and he realized to get the kind of precision he had in mind, he needed 25,000 observations. So they are too crude to be used as what happens at a particular end. Don't believe us all these asymptotic
Well, big assumptions. I don't quite agree with this. For example, when you're doing a two-test between means, it tells you that the variances must be the same. If your sample size is approximately the same, even if the variances are very, very different, robustness holds. It doesn't have only to do with normality. Sometimes the F-test, for example, is very robust, even if the variances. So it's not. It doesn't have to do only with asymptotic properties. Sometimes, even with small sample sizes, various robustness takes place, and we have to know what tests are very robust and which ones are not.
Neither the t-test, not the f-test, nor the chi-square test are robust to heterogeneity or certain kinds of dependence. None.
But they're robust to variance, inequality in variance?
Yes, exactly. As long as it's kind of symmetric, you get by. I mean, you get approximate results, but okay. So it's not that you, let's say...
There are whole books have been written on robustness.
I know, but...
Big books.
Don't get me into those books. So, the objective. very quickly, because I want to at least touch a few of these big problems, is to learn about this statistical generating mechanism. Statistical. The truth here is basically saying, is shorthand for saying this distribution, the joint distribution of the sample, could have generated this particular data. It's not truth in this, let's say, metaphysical sense and all of that. Could this generating mechanism have generated this particular data? And we want to learn about this unique value that this data point to. So that's really very important for all the rest of the discussion. So here, two kinds of reasoning. Estimation reasoning. When we do estimation, and we come up with the sampling distributions, the reasoning we use is factual. We evaluate the distribution under the true theta star, whatever that happens to be. We don't need to know it. So that's the factual reasoning. And that involves point estimation and interval estimation. That's extremely important because a lot of people sort of seem to forget that. What happens in testing? Well, we use hypothetical reasoning. When we say under the null, we basically say, what if the null is the true theta? Then we change it to an alternative and so on. That's hypothetical. We decide the value. We never know the theta star. And if we don't separate those two, we are going to get confused between this result here with this result here. Very easy to get confused. So, the psychologists left, but they do it all the time. So, I'm going to come back to that. It's very, very easy to confuse the two if you don't really put anything there because it's obvious. It isn't. Look at a lot of textbooks and ask the textbook writer, what do you mean? That's an unknown parameter. What do you mean the mean is 0? That can only be 0 if the expected value of x bar equals that unique value. That's the only occasion. And that plays a huge role later on. So, here I have the example psychologists love. And I can show you what kind of trouble they get themselves into. So, of course, the testing is trivial. So I'm just playing around with the null and the alternative, the central versus the non-central to the scheme. There's nothing there. But then they start playing around with these pivotal functions. They write this like that. Of course, that's an unknown parameter. And then they tell me they found a non-centrality parameter. How? I mean, if this is the basis of the confidence interval, you're actually evaluating this under that mu equals mu 0, or gamma here, which is the difference, equals 0. That's the testing part. Equals the true is a completely different animal. But there are chapters and books written how to get confidence intervals out of a non-central student-C distribution. Remember that duality between, the mathematical duality between tests and confidence intervals?
This is hypothesis testing. This is confidence interval where you're not assuming any hash node or anything. I'm aware of this procedure and the book also. That's quite kosher. There's nothing wrong with that.
So what do you estimate? What is the underlying reasoning?
This is not evaluated under any null or anything. Your gamma is not supposed to be 0 here. You don't know what it is.
Yes.
It's not it's different from hypothesis testing. You're building a confidence
interval. But you have to tell me why this gamma, which is a known parameter, doesn't have value 0 or something else.
Yeah, it's not 0 here. That's why you have if it was 0, your non-centrality parameter would be 0.
But that's what I'm saying. If you're doing confidence intervals, you're using factual reasoning. It says, when this is the true value and I evaluate under, I get 0 there. When you do testing, that's a different ballgame. Of course, everybody is aware of what happens here.
Yeah.
But there, you're varying the value at will. This is a test statistic. This is not a, let's say, a pivot. So that's how these non-centrality come in. And of course, there are books and books and all of that. It really doesn't make any sense. So there are some psychology guys there, and I show how they should do it to avoid that. So we get to this theta, the observed value of a point estimator is close to theta 0. And of course, we all know how to get a good value for that, which is to go to the empirical sampling distribution with then 10,000 replications to get something which is close to the true value. Any single value is not going to work. So if I have that empirical distribution, this thing here, then the mean of these 10,000 replications of sample size 50, that's how I get to the true value. Anything else will not work. Why? Because any one of the 10,000 could be down here, could be down there, or anywhere in between. Could it be very close to? Yes, by accident. So we shouldn't be ever going to this jump from I have a good estimator. Yeah, it has a beautiful distribution, it's unbiased and everything else, but that has nothing to do with what happens at x0 when you evaluate that particular formula. Because it can be any one of those values. And of course that translates to observed confidence intervals, and I have some examples there, but I want to emphasize these effect sizes because that's what they are doing. I'll come back to it later. So this is the difference between testing within neyman-pearson testing. You have a pre-specified statistical model. This is the set of all models that could have given rise to the particular data. And you assume the true model is here, and you're testing with it. That's why you partition it and try to narrow it down. Here, this is your null. The whole model, not one of the assumptions, all the assumptions. What is the alternative? Everything else. Now you can see this is unmanageable, of course. So you have to find clever ways to probe away from your model in order to detect the discrepancies from your model assumptions. There are many ways to do it. You can do encompassing models, you can do directions of departure, and I have papers and books to explain all of those things. But you have to do a great job here. Now, non-parametric tests are very useful here because they have broad scope but very close to the null. So they're searching here. Now, what happens when they detect something? That's excellent evidence that something is there. They don't tell you what it is, but they tell you something is wrong here. So tests with low power, like non-parametric tests, are actually damn useful in misspecification testing. As I said, you just cannot rely on only non-parametric tests, but they can give you a buzz. Be careful, something wrong is here.
So why in principle is the thing on the right not neyman-pearson? It just has a bigger model.
Because to get a neyman-pearson, you have to partition your, yeah, I mean, this is a partition, but this is every other model that could have used the rights to your data. So how do you probe?
So the way we're talking, neyman-pearson has to be a parametric.
Yes.
And on the right is non-parametric.
Yeah, one of the ways to do it is get a much larger model that parametrically nests this one, and then you have everything you have in neyman-pearson. But the interpretation is different.
Why is it the whole big box?
Because you cannot parameterize every possible statistical model. I mean, that's the reason.
So the difference is really between parametric and non-parametric.
Even non-parametrically, you cannot really probe the whole thing. Even non-parametrically, you cannot do that.
The right is like Fisher and the left is Neyman-Pearson?
Well, in a crude sense.
That's in your
Yeah,
book.
one way of looking at it. But this is unmanageable. You have to find ways to manage it. One is to embed it into a bigger model. That's why people test for the Napi-Watson test. They have a white noise error. They say, no, it's a autoregressive of order 1. Then that encircles this into a special model. But the interpretation of your results is completely different. So there's a whole, let's say, gamut of differences here that I don't have to get into. But I have published papers where I take you through piece by piece. Yes?
I'm sorry, can I go back to a slide back? Just one comment. A slide back, not this one. No, that's just previous.
The previous one?
Yeah. So this histogram, right? This is a target distribution. Yeah. Actually, in my work, it's actually is a continuous distribution. So the question I want to ask you is that is your error distribution, is that error, what is error distribution? Is this kind of severity function, is this your severity distribution?
No.
Okay.
The severity bound function doesn't need replication.
No, it's not replication, your target is this one.
No, it
Okay.
is back to the original data and the possible values of the data. It doesn't involve sort of hyper distributions. Here, you have 10,000
I know this is
Yeah,
you don't
replications
never
of
have
original
this,
data.
but
Yes.
this is your target. You try
Yes.
to measure the uncertainty. Is that
No.
severity trying to capture this uncertainty?
It is not by replicating the original
Oh,
distribution.
yeah,
This is-
yeah. You don't get that one, but then
Yes.
is your
I'm going
target
to-
trying to capture that one?
I'm going to skip this. You need a partition to go with the partition of the parameter space and the accept reject. I think we shouldn't do. Here is where I disagree with the literature. And this is where the two different kinds of perspectives on the p-value simply introduce another level of confusion. If you're using the p-value in an neyman-pearson setup, inevitably, you're going to look at this definition, which says the probability of obtaining a result equal or more extreme than the observed value of XO when H0 is true. Because equal or more extreme, you define it as H1. So you run into this pre-data problem. So you have two-sided p-values, and of course, if you're very careful, if you have a positive large value of the test statistic, which increases with the discrepancy, you shouldn't be looking on the left hand. How do you avoid that? Different definition. So the post-data definition basically says the p-value is the probability of all sample realizations for which dx0, this is the test statistic, accords less well with h0 than h0 when h0 is true. This is one-sided every time because it's bigger or less than depending on, let's say, the sign of your test statistic. So you don't have two-sided there. Then, of course, here I have an example where it's easy to get confused totally. So here I have three different specifications of theta. This is the Bernoulli. I'm going to use it with real data later on. And here are the statistics you need. Nothing really is very important there. And then, of course, you have three different rejection regions. So if you use the pre-data definition of the p-value, you have three different values. There they are. And you say, well, one accepts, the other rejects, or the other two reject. What is going on and which one is the relevant p-value?
This is going so fast that I don't think I'm following it, and maybe other time too. It sounds like it's something that might be central to your...
Okay, here I'm backtracking. So, theta is a value between 0 and 1. I have a Bernoulli model, simple Bernoulli, Bernoulli IID. I frame the nullity alternative as one-sided and is less than or equal to and bigger. Then I reverse the inequalities. Another formulation. And here is the two-sided part. Theta 0 is the only common set. What are the optimal tests that go with these three different formulations? Well, they have the same test statistic, but the rejection region is different. So when you try to get the p-value out of these rejection regions, you're looking at this tail or that tail and let's say the two tails by the definition of the traditional definition of the p-value. So here, this is what you look at, and you say, well, wait a minute. The first is reject, the second is accept, the other is reject, but which one is the relevant p-value? The truth is, they don't agree actually. They basically tell you that theta star is not in between 0 and 0.5. But that's too crude to be particularly useful. So the p-values and the accept reject, the way we use them, are really back to this very crude level. Now, there is not
Not
totally
not for the second, right? If you look at the p-value, the p-value is close to 1
Yeah.
for 2.
Yeah, because
So
of
you
the
are
way
not going
we,
to reject,
yeah.
you're not going to reject the null.
Yeah, because it was bigger than and less
Right,
than.
right.
I reversed inequalities. So, but they tell you the same thing. Theta star is not in that range. In other words, it's in this range. That, if you look at them closely. But that's too crud. That's where severity comes in and say, at the severity of 0.85, this is really shrinking of that.
So
enormous.
severity is a synonym for confidence.
Yeah, well, I'm going to show you the coefficient interval later. It's not telling you that. It's actually, the coefficient interval, it doesn't even overlap too much with that. Anyway,
is
how do you get
confidence interval is confidence of this?
No.
Severity.
The coefficient intervals and severity might agree on a point, nowhere else.
No, we're not talking about confidence interval. We're talking about confidence in this range.
Now here I'm jumping the gun. I'm going to show you how to get this. I'm simply saying that the value of severity is that it takes this very crude answer you get from accept rejection of the p-values and tells you this is what you should be looking at with severity 0.85. That's my point. It's not that I'm doing anything. I can show you how to derive this in a second or two. So I'm going to forget the long run metaphor because it's a lot of... here is one of the biggest problems. This is the conditional probabilities and what goes with it. I got involved in this controversy with the base rate fallacy because if you misinterpret error probabilities as conditional, you get into this mess of evidence and hypothesis and reverse and all the rest of it. They have nothing to do with it. Yes, these are very useful things, but not in frequentist inference, and especially frequentist testing. So this is a published paper, it's almost 10 years ago, but here is where it's relevant for the discussions with the famous PPB. This is based on 3 statements. H naught, no disease. Gamma equals 0. Let's pretend we're playing that game. Then H naught is false. H naught is false is not an event we can condition upon. Okay? So when we start conditioning, we get into trouble. And of course, this is an event. It rejects because it depends on the x. So this is how we play this game, and we use this analogy of the false positive and false negative for medical devices. What people forget is how we establish this, let's say, rates for, let's say, medical devices. We don't have a real data and muck around until we establish. We are in a lab, and we have 10,000 specimens that, let's say, some of them have the disease, some of them don't. We create them in the lab. Those are events. We know whether this is true or false, whether the disease is there or not. And then we calibrate these medical procedures. Nothing to do with error probabilities the way we understand them.
Now, hold on, you're saying that it does not make sense to, when we, for example, when we calculate our type 1 error, for example, is the probability of rejecting conditional and null. You're saying it's not a condition?
There's no condition on
It's
anything.
conditional.
That's where the problem is.
In frequentist, we don't have parameters in
No,
event.
we can't condition on theta equals 2 or 3 or 5 or 8.
Because it's not an event.
It's not an event, it's not a random
Either
variable.
it's true or not.
Yes. And it's under this scenario we evaluate the sample distribution. Now, error probabilities, not only are they not, but they depend on this context. Take them out of this context and you have nonsense. So don't buy that analogy. It doesn't really come even close. Yes, it's attractive. It looks as though we're talking about the same things. We are talking about apples and sausages, not even apples, oranges. I mean, really nothing to do with each other. So when Ioannidis published that famous paper, almost all published empirical results are false. The Nobel Prize winner with Virginia Tech, G. Buchanan, called me up. I was in Europe, because for years I was telling him that empirical evidence in economics is terrible. And I thought he established that by replicating dozens and dozens of studies and showing that what they're doing is actually false. No. He sat in his office and basically said, well, why don't I assume that's 20%? This is 80%. And then came up with a number. Really? And of course, this number is field wide. So if I did a great job with mine, testing my assumptions and doing all the rest of it properly, I'm guilty of producing, let's say, untrustworthy evidence because I'm an economist. I mean, it makes absolutely no sense to me. None. My results depend on the context. You cannot take them out of context. The 5% and the 80% and all that have nothing to do with me because of these reasons here. And of course, I cannot attach a probability to F and things of that sort to read them out. So here I have a few more things, and I explain where this comes from and how these really have nothing to do with anything that we are interested in. So here is the false positive and why they are actually events. I know that this specimen has cholera, this doesn't. And those become events. So I'm going to skip this. The small n problem, as I said, if you don't have a large enough sample size to test your assumptions, forget the inference. And here is the large n problem. Here is what happens when you change the number of observations. Here I have a very simple thing. And here I have observations from 0 to 1 million. Now, I've attended seminars with 6.5 million and 5% significant level, and things of that sort. What happens? Well, your test becomes more and more sensitive, and this, at 10,000, by the way, sorry, 1.5 million or 2, is close to 1. I couldn't put them together because they really take forever to, but this is what happened. You're picking this thing, and you think it's a great discrepancy. So this is not the usual picture of power, where you're down here you have the parameter for the alternative. This is fixing, let's say, the discrepancy and looking or changing the sample size. You can be picking up tiny, tiny 7 decimal places and you don't know it. And that's the problem with the p-value and taking the accept reject out of context.
The y here is this, is that alpha? That's
Yes.
significance level, is that what it is?
No, this is gamma. This is the discrepancy. The discrepancy from the null. So here, this is what's doing the work.
It's an alternative.
Yes, the difference between mu0 and mu1 is the gamma here.
The gamma is indexing a alternative hypothesis.
Yes.
Is that right?
The difference between, but this is what is doing the work. This is really the power of the test, which says you're going to pick up this discrepancy of 0.02 with less than 1 million observations. No, this is 100,000 actually, less than 100,000. But then if you go to 1 million, all of this hit the 1. You're going to pick it up. And you have 5 and 6 decimal places. So this is really the context I've been talking about, and in particular that really goes wrong with whatever it is. So how do we address this issue? Well, rules of thumb. Neyman and I.J. Good came up with different, Neyman and Romano basically say, well, as the sample size increases, reduce your alpha. Use, in other words, this trade-off between type 1 and type 2 errors. Good says standardize your p-value to n equals 100. And it gives a particular formula that, of course, neither really works in practice. And this is where the estimation-based effect sizes were born. Fortunately, the psychologists have gone. But this is how they tried to explain it, and Abelson is actually one of the better ones. One advantage of the raw effect size as a measure is that its expected value is independent of the size of the sample used to perform the significance level test. So it's not a coincidence that a lot of these effect sizes, if you go to Cohen, is test statistic and he kicks out the square root n. So wait, you don't even have a distribution now. How on earth do you consider that anything valuable? So the reason is they're playing this is what they are invoking. But this is for the estimator, it's not for the x0. And of course, we know how to get precise values if we replicate the data 10,000 times. But once, you cannot really come even close. So this is part of the lack of foundations for these effect sizes. And of course, I've done it for the difference between two means and show these not centrally gate parameters are really terrible. Then replace with the p-value. People say it's less vulnerable to the large n problem and is more informative because it provides a measure of the effect size. Really? This isn't going to zero as n goes to infinity? I mean, this is really how we evaluate good and bad confidence intervals.
Now,
Expected size.
you keep saying observed confidence interval. Is there any, what is the observed?
Yes, the observed means replacing the capital X bar with a small x bar.
Oh, I thought all confidence intervals were observed.
No. This is where we attach the probability. It's the capital we attach the probability to. So the minute we replace it with the observed, there's no probability.
Well, that's the usual effect size that Cohen is referring to, is your t-statistic without the square root of n. And it's like, for example, x1 bar minus x2 bar divided by s.
2-point estimators.
Right, right.
Why would you believe that?
These are orders of magnitude. For example, I can tell you, when this number is close to 0.5, that's a medium effect size. I mean, Cohen has spent his whole life. He's written a big book like that.
Yeah, I have a book and I spent a lot of time.
0.8 is large, 0.5 is medium, and 0.2 is small.
Yes, I'm going to show you another example where the small, medium, and large is
He
really.
just makes that up as a.
No, it's not made up. It's based on thousands and thousands of studies.
So, attempts to assign probabilities to observed confidence intervals.
In certain areas.
So
Yeah,
here
that's
is the observed confidence interval, Glenn. I take this expression.
I just wasn't familiar with the adjective observed. I thought only observed ones were called confidence intervals.
No. Observed means the value you place on. Sorry about that. What happens if you put a mu 0 equal to that? You solve an equation and you get the p-value. So you put mu 0 on the boundary of this confidence interval. Boundary is here because it's two-sided. And you solve it. The problem is, halfway through, you switch the small x with the capital X. That's the problem. So there is a lot of issues that come in here, and a lot of solutions, including these confidence distributions and all of that. And here is what happens. What happens if we put, instead of mu 0, a mu 1, and then allow mu 1 to change, we get these beautiful diagrams. One is upside down, the other. The question is, are these legitimate probabilities or legitimate? Thank you. They're not. We are confusing ourselves. Who was the first one to confuse himself? Birnbaum. 1961, publishes a paper. He wants to unify testing and confidence intervals, and he comes up with what he called an omnibus confidence curve. And he gives us exactly what he means, and he's doing exactly what I showed before. Stick the m there, and then solve it. And of course, Kempthorne folks, many years later, do the same thing. And those come from their pictures, by the way. It's either upwards or forwards. And then Poole came in and provided us with a p-value curve. They are all in the same boat. Here, the biggest confusion is switching between factual reasoning and hypothetical reasoning, and not exactly knowing exactly where these probabilities come.
But you don't have to confuse yourself. I mean, I don't know that Birnbaum did. You can just say that the particular interval was the result of a general method that covers the true value 95% of the time or whatever it is.
Right.
Yeah, you can say that for the random interval.
Yeah, I think this is not,
Anyway, I don't have time to really elaborate. I can send you a whole paper where I take each one of them and show exactly how they derive theirs. And of course, these are not legitimate error probabilities or coverage probabilities, or the kinds of things that we associate with tests and confidence intervals. They are the original distribution under the null reshuffled in some number of ways. So please look at it closely, and you will see there's no non-centrality, there's nothing there. There's no real evaluation of mu different from mu zero. It's the original under the null, and you reshuffle it, and so on. So I will leave you to play around with that, and spend at least 5 minutes on severity, because I owe it to you guys to show how this works. So, the definition, of course, is straightforward. It talks about S1 and S2. X0 accords with H, and it can be H1 or H0. And S2 has the two negatives. With very high probability, this test will have produced a result that accords less well with the one that passed, depending on whether it's an alternative, than H0 does if H were false. And this is in the 2006 paper. So, here I have an example. The alpha there is for a reason. I'm testing this ratio of boys and girls. Theta, in this particular case, is basically the probability of a boy. I mean, it's slightly bigger than half. And I have real data, and very accurate data. And I apply the test, and of course, I get a rejection of the null. I've already done that test before, but what I care about here is more the sign of the test statistic. So, the sign tells me that the relevant inferential claims that I should be looking at from the post-data perspective are that theta is bigger than the original, plus a discrepancy positive here because of the large value, positive value of the test statistic. So this is what tells me which direction to look at. Then I translate the two conditions. So I rejected the null. That means the data accord with the alternative. Then I go to S2. I need all outcomes for which this particular test accords less well with H1, because that's the one that passed, than H0 does. What does it mean? It has to be less than what I observed. Because if it's bigger, it actually reinforces, it becomes more in accordance with. So these are the events I need to evaluate under different values of theta 1. I have to vary gamma and evaluate these probabilities. How do I do it? Well, there is an observed value of the test statistic, and there is a non-centrality parameter, which basically combine. I take this value, subtract for different discrepancies. I have to be careful with that, but this is very close to 1, so I can ignore it. And this is what happens when my discrepancy is 0.01. Remember, this is 50 is the null, 0.01. This is the tail area less than this difference. In other words, less than that 1.5. And I do that for all values of gamma.
Okay, I believe your severity function, or the function of theta 1, is the exact confidence distribution. Yeah, so you get the number. So whatever the severity calculation is, confidence distribution, you produce that.
Yes.
Confidence curve is one of the things.
But that's where the p-value comes in. The p-value is evaluated under null, but it depends whether you go left or right there. So here is what happens with the evaluations. So 0.1 is very large, 0.12 or 0.12, and it decreases. I have to decide and defend why I'm basically chopping the 0.85. That is, like every other inference, the part of where we can debate and disagree with. But here, because I only had 10,000 observations, I didn't want to go to 0.95. This makes more sense.
So with gamma is with a 0.01, your severity is 0.94.
Yes.
And what was your p-value is very small in that case?
There's only one p-value.
What is it?
Well, in this particular case, it's 0.005.
Yeah, so that's a problem, don't you think? Because what's going on is that you have a very small effect size. Your p-value is small just because of your huge sample size.
The p-value is looking at the wrong tail.
But it's looking, it's a function of a sample size. It's very small because of the sample size.
Yeah, I'm looking as well, because when I evaluate this, I have the non-centrality parameter, which is what plays a role in the...
Yeah. Don't you think the evidence is very weak here?
Yeah, this is where severity picks up the effect from the sample size. It's part of it.
Right. But don't you think the evidence is very small when gamma is going to 0.5? Very, very strong. The difference is quite immaterial. It's significant, but it's immaterial.
Here I'm looking for the biggest discrepancy I can justify on a high severity. So, yeah, I can justify the small discrepancy, but that's not what I'm interested in.
I'm saying the difference is unimportant.
Yes.
And the severity test doesn't pick that up.
I'm interested in going as far to the right as I can, not here. So, this is the line, and this is basically roughly where...
No, but can you address the issue that with gamma is going to 0.01, the difference is significant statistically, but not important?
I'm going to do another test. This is a post-data evaluation of the test I already did.
All right, but the difference is not important, right?
It is important.
No, it's significant, but not important. It's 0.51.
I don't worry about that until I go to the substantive significance Prakash.
Just
So-
instead of saying important, you could say warranted. We don't know yet if it's.
Whether it's statistically significant and substantive is a different issue. I haven't even addressed that. So here I'm playing this game and say statistics will take me this far for that thing. Now, that gives me an upper bound. It cannot be bigger than that. So it gives me an upper bound there and then say, well, do I have something from human biology which tells me this number? And the answer is yes, I do.
So other people would have calculated a confidence interval and then looked at whether it was substantively significant. Well, why do this? Why do something?
Here I have a particular value that I know what substantively significance is, and I will give you the value in a second.
You weren't going to go there yet.
Here, biology. Yes, I'm saying I can distinguish between statistical and substantive
I
significance.
understood that, but before you get there,
Yes,
well,
statistics takes me as far as that discrepancy.
this new kind of interval, this severity interval.
Yes, this is what, as far as statistics
Why do
are
we
there.
need that when we already have a confidence interval?
Because the confidence interval has nothing to do with any of these calculations. Have you ever evaluated the confidence interval with a non-centrality parameter to take account of the sample size?
Yeah.
I haven't seen anybody doing that.
The confidence interval have the issue is that you fix level of test. So if you want to
You
make a
fix
decision, level of significance, right? 95,
Yeah.
0.05. Why is 0.05? This severity function will give you all possible kind of choice, possible values.
We had to choose a number here, 0.85.
If you make decision.
Yes, but you
If
can.
you make decision. If you don't make decision, you give the whole picture to us. This is the same thing as a confidence interval.
There's a one-to-one correspondence between whatever these numbers you see here with the set of possible hypotheses you
Yeah.
could have done.
I'm
Namely,
going to give you.
if you just stay over
I can
here,
give you.
I can tell
I'm
you,
going to give you the whole thing.
if you're
here is-
testing, if
you
you're
talk about
testing
If I were
0.51,
to draw the line here and then look at substantively significant, what am I going to find out? This is a curve. This is not just 2 points or 3 points. It's the whole thing.
Yeah, this is the whole picture.
Yes.
but you could read off essentially a
Yes.
whole class of tests you might
You
conceive
can.
yourself doing
But-
from here.
Can I say just one thing? That
Sure.
confidence intervals lacks an adequate interpretation because of the fact that at most you can say it came from a method with certain coverage probabilities. Once you give it the testing spin, which severity gives you, you'll say, why do we say that that there's evidence that mu is greater than the lower bound of the confidence interval? Because if it was less than, if mu were less than the lower bound of the confidence interval, with high probability we would have gotten a larger difference than we did. My point is
This is,
that even where you get this match number,
this is
0.5,
within
1,
my
2.
upper bound, yes. So here I can look people in the eye and say, at 0.85 severity, the warranted discrepancy is slightly bigger than the biologically determined discrepancy, so I can claim substantive significance. One of the reasons I use this example is because I have something concrete to compare it to. This is a whole book about that particular issue,
So
and they're all kinds of...
0.51 to 2. Can we go back to the table and see where that is?
Yeah.
0.51 to 2.
Here is the...
0.51.
Yeah. I'm just going slightly bigger than that, but that's all. That's why, that's the threshold there.
So your severity should be higher than 0.85 for
Well,
how do you...
no, this is, if I determine 0.85 for a decision, as correctly was said, I would say it cannot be bigger than this discrepancy. It cannot be bigger than that. There's an upper bound there. And that's why I look whether that upper bound includes the substantively significant value. Now here I do devil's advocates and change the null and the alternative and muck around. I don't have time to go through, but the severity doesn't change at all. You can change your alpha, you can turn the rejection to an acceptance if you want, but if it's positive, you're looking at discrepancies on the right of that, and so on. So here I do that with a different value instead of 0.5. This is Nicholas Bernoulli. Around 1835, says it's not half, it's 18/35. Basically 18 boys to 17
That
girls.
was a response to the odd nut paper.
Yes. And I'm saying, would anything change if I change the 0.5 to that and test again? Yes, these numbers are exactly the same. No, nothing is going to change. The discrepancies will change because I'm starting from a different point, but these numbers are identical to the previous. So now that will happen, and this 0.05 versus 0.049 and so on nonsense doesn't work at all. The severity is not going to change. It's not going to be affected by accept, reject, and all of that, sharp dichotomies and all that jazz. And of course, how do we address this fallacy of rejection because of the sample size? Here I show the relationship between, let's say, the p-value and the severity evaluation, which is under the null, basically, what you're pointing out. But that's not what we're interested in. We need under the alternative, so we'll be able to have information about the sensitivity of the test in picking up and taking that into account. So that's the reason why this is important. And here I have a nice example to show you how the sample size comes in with the severity here. So I'm interested in this discrepancy of 0.2. If my sample size is only 50, the severity of that point is close to 0.95. But if it's 150, it reduces to 0.8. If it's 400, it's 0.5 or very close. If it's 1,000, it's tiny. This is the sensitivity in action, because I'm using the non-centrality parameter with the sample size in order to shrink what you're warranted to claim about the severity of this particular discrepancy. Of course, we have diagrams where we change the discrepancy and so on, but this gives you an instant picture of how this evidential account, if you like, takes that fully into account. Here is where I compare the severity with observed confidence intervals, and basically say that the way we do it with Deborah Mary in 2006 is actually to replace the gamma with some of these numbers that come from confidence intervals. Because we are looking at a discrepancy here. And we said, what if the gamma relates to this number here or to that number there? But then, of course, we showed that different points within the confidence interval have very different severity. And in particular, this has always severity 0.5, very low. And then we show how you can actually evaluate the severity of the inferential claim, bigger than or less than. But that has nothing to do with the coverage probability. Absolutely nothing to do with it. This is testing reasoning and is under the alternative and so on and so forth. So it's testing reasoning, and of course, the coincidence at the endpoints is not the answer to it. So yes, there is mathematical duality between confidence intervals and hypothesis test, neyman-pearson test, but it's a mathematical duality, not an inferential duality at all. One goes with the coverage probability, the other goes with power and type 1 errors and all that. Yes, we are looking at tail areas which are the same, but the reasoning and the interpretation, because we don't attach probabilities to theta's, we attach probabilities to the inferential claims. And that is, the probability remains on the procedure, the testing procedure. It's not leaving that and goes and touches itself on the theta. Yes?
So kicking back to your table, here you can claim it's not coverage. It is different than the confidence interval for this one, right? Just that.
This is when I switched.
This table. Okay. So if you're repeating the experiment millions of times, I believe that if you would have 82, you just look at the whatever the one is the 852. That's the third column. So you will 85.2% of them will be bigger than that the 0.512.
I agree with you.
So that is confidence, the interpretation of that.
You're going to reject the hypothesis that
Right.
512.
I know what you're saying.
Yeah.
If I replicate in the usual way and look at the tail areas,
Right.
I will get the
This is
result.
confident, yeah.
Yes, but you have to be very careful because it won't work because dx0 is data specific. You have to be careful. So
Right.
for the type 1 error, yes, because you use the uniformity under the knob. For the alternative, the distribution is skewed, so it changes. You have to be very careful.
Under China, yeah.
Yes.
Under the true, exactly same model you repeat.
That's okay.
Then that's confidence, right?
Right.
In that sense, right?
Under the true,
Under true,
yes,
yeah.
we are on the same
Yeah.
but not when you change new at will.
Yeah,
And that's
that's
really the
different. Yeah,
difference.
that's different. You have different model, right?
Yeah. Here again, we've seen that. Let me see whether there's anything interesting, and then I'll. Yes, this is comparing data from Cyprus in 1993 and Avputnos data for 1634. I chose that date because the sample size is very close to the sample size I have for Cyprus, which was around 10,500. So I do the severities for both the warranted discrepancies and for 0.85, this is what I get. Very close upper bounds. That for me is a kind of replication. There's no reason why that phenomenon was true in London in 1634 and in Cyprus in 1993. And I want to relate some of this to more broader, let's say, data sets. Summary, replicability, let's disconnect the two because we are confusing ourselves. The problem is not just abuse of p-values and all the rest that goes with it. It's much more broad, and I summarize there. And of course, these observed confidence intervals and estimation-based effect sizes are really vulnerable to exactly the same things. So the misspecification will mess them up completely, and some of the rest of those problems will affect those in the same way. And of course, the post data at this point is the best tool to get an evidential interpretation that can be used to talk about statistical versus substantive significance and solve a lot of these problems that neyman-pearson was suffering for the last, 80 years. So this is what the error-statistical perspective is trying to do. It's broad enough for anybody to address these 1, 2, 3 problems that I raised above, and the different ways that untrustworthiness can come into your evidence, bring out these common sources of confusion, frequentist inference, and then there is something psychologists call null hypothesis. Yeah.
And it's just,
And I don't recognize what that is. And I've been teaching statistics for 40 years. It did not need to do with, this is a caricature that really enables them to say all kinds of things. And of course, the post-data severity will help solve some of these outstanding problems that have been around for ages, of course. The Larson problem has been around since 1938. And both Carl Pearson and Fisher had a go, but neither was able to explain what's going on. Thanks for your patience. I know it's late.
So who called it the Larson problem?
Because when Bergson brought it up, he basically says,
Did he call it that?
yes. He basically says, when I look at the results of these tests, all I can deduce is the sample size. Every time the sample size is large enough to reject.
Which person said this?
No, this is Bergson.
Bergson.
Yes.
psychologist.
Yes. 1938. But he provoked both Carl Pearson and Fisher in a change in early 1930s.
Oh, yes.
So, I think a couple of things. One thing is the graph was talking about. I think what the histogram is actually is a sample distribution, not a C. It's also not your severity, but it's a shift of the severity.
Are you talking about this graph?
No, not like the previous. Yeah, the histogram. This is why I'm going to come back to the second question. Actually. Yeah. The first one is the only one. Ask the question. I mean, ask the question.
Okay.
That one actually is not CD either. It's
No, I think it's before.
yeah, before that. That's more. It's a shift of the CD. It's a shift of the CD, and also this is sample distribution actually, right? The empirical sample distribution of beta 1 hat.
Yes.
So then that's a CD is a shift of that. Your severity also is a shift function of the too. So you set it to the observe the beta 1 hat.
You have to do the replications for the discrepancies.
Let's put your severity function, take derivative, the density version of severity function, plot it over here.
It's not going to work unless you put beta 1 plus the discrepancy and redo this, because otherwise the tailors you're looking at are moving with the discrepancy.
Yeah. So that's what I'm saying, is that so you have observed the beta hat, so you're going to peak on the beta hat, but the tail part is going to be, your function is going to be exactly the shift of this distribution.
No, it's a tail area. You're absolutely right.
Yeah.
And
So
once you
that's
have
basically the same
the
thing.
tail area
You take
replicated,
exactly mathematically exactly the same thing.
Yeah.
So that one is actually exactly CD is going to be there. So one-sided common distribution. Common distribution is going to be there. And the other one is that I think this is I seems more convinced that severity is a common distribution, and the common distribution is a severity function. Yes. And the second thing is that you mentioned that the problem with the confidence curve. The problem of confidence curve is two-sided test. So it's not giving you the right story. So if you do
I did the one-sided, yes.
No, if you don't do the confidence curve is always two-sided. If you just do one-sided confidence distribution,
I have a whole paper on this.
then it's going to
One-sided,
be exactly the same as
two-sided,
severity.
and compare them. They give the same numbers, whether you look at them through the p-value curve or reverse the way you're looking at it.
Right, yeah.
Because there's a trade-off between the alpha changing with the alternative, and of course, you're just picking up that trend.
No, exactly mathematical expression is exactly the same. One side, the confidence distribution is exactly the same as what your severity function.
With the severity, we always have that issue that is the problem that matters. It's not. It's the reasoning and how you interpret the results. So I agree that there is family resemblance, and we can discuss that. And we can see some of the common, let's say, or the overlap between the two.
What you're doing to get the equivalence is you're switching what you're testing, and Aris doesn't like that. I'm more inclined to allow that.
Okay.
You're hypothetically saying, were I to be testing this, what
confidence
results would,
yeah,
you know what I'm saying?
yeah, I know what
And
you're
that's
saying.
what you have to do,
Aris,
to make the duality.
I'm going to ask you a question that, I've checked the literature and a few people in the literature have leveled a charge against severe testing. I did ask the question with Deborah, and I want to know what your take is. The common criticism has been with base, have you read about it? A lot of authors have said it, the base rate fallacy. So you have a test that has a very high sensitivity, very high specificity, and it's supposed to be, the test is supposed to be very severe, but because of a base rate, you have a very low posterior probability.
The problem is false positive, false negative has absolutely nothing to do
So that's why you said that at the very start, right?
Exactly. It's nonsense.
But have you seen the criticism?
Yeah, I published papers on this.
On the criticism of the
Yes,
base rate? A lot of
the base
have
rate,
read it.
exactly. And say, stop it. I show them what the test looks in that context and all these other nonsense that they throw around. Have nothing to do with conditional probabilities, nothing. But error probabilities are not.
So you've addressed that in a paper?
Yes.
You sent it to me?
Yes, I will.
Okay.
Thank you.